Hi, I'm Kamaya.
Hi, I'm Anya.
And we will be discussing the SN1 and SN2 mechanisms. So, SN2 stands for Substitution Nucleophilic Bimolecular Mechanisms. It was discovered in 1896 by a German chemist named Paul Walden that discovered that malic acid could be interconverted from the negative enantiomer to the positive enantiomer after a reaction with PCl5. Today, as I stated, it is known as the nucleophilic substitution, and it involves the substitution of one nucleophile for a leaving group, and it is very useful in synthesis reactions. So, some things to know about SN2 reactions. The first thing to know is that it is a one-step reaction, meaning instead of undergoing a carbocation intermediate, it has what is known as a transition state. And in that transition state, the geometry of the molecule changes from tetrahedral to trigonal bipyramidal before returning back to a tetrahedral geometry. So for SN2 reactions to happen, you need three things. You need a good nucleophile, you need a leaving group, and you need a methyl or primary substrate group. And that is because the reactivity of methyl and primary substrate groups are exponentially bigger than other groups, as you can see by this chart below. And it is important to note that vinyl and aryl carbons do not undergo SN2 reactions. So, as I stated earlier, you need a good nucleophile. What is a good nucleophile? As shown in the list below, good nucleophiles are typically smaller and more negatively charged. Some examples are halides, as you see in this list, RS groups, and OH groups. So, the reason that geometry changes is because SN2 undergoes something that is known as backside attack. So with backside attack, the nucleophile, which is what is negatively charged, as you can see here, will come in backside of that carbon where the leaving group is attached, and it actually kicks out that carbon, which interconverts all the groups to the other side. And to show this in an easier way, we invert the stereochemistry of the nucleophile data, as you can see right here. The wedge turned into a dash, representing R to S.
In the instance when you have a weak nucleophile or a hindered substrate, such as a tertiary halide, the SN2 mechanism is not going to work very effectively. And so that's where the SN1 mechanism comes in, and that it provides an alternative pathway to the SN2. So as we can see here, we're starting with the same bromobutane as we did in the SN2 example, but the difference here is the nucleophile. Water is a super weak nucleophile, and in this case, it's also acting as its own solvent, which is a process known as solvolysis, which is very common in SN1 reactions. So, to demonstrate the full mechanism of this, we're going to first start off with our starting material, the bromobutane. And in the first step, the leaving group all by itself just kicks itself out, and this is the slow/rate determining step. And so that will lead to a carbocation intermediate. And I should mention here that since there's a carbocation intermediate here, rearrangements definitely can and will occur if it leads to a more stable product. But in this case, everything's secondary or primary, so no rearrangements will occur. From here, the nucleophile will come in and attack the carbocation, which will lead to this. And the stereochemistry is going to be racemic because the nucleophile can attack from either the front side or the back side. And so since the oxygen is positive and we want to get rid of that, we're going to do a deprotonation step. So we're going to have the H come there and here, and that'll lead us to our final product of 2-butanol. And once again, racemic mixture, which is a characteristic of SN1 reactions. Some things to remember with an SN1, you're going to have racemization, so inversion and retention of stereochemistry in your final product. Substrate stability is interesting in the sense that it's directly the opposite of SN2 reactions because tertiary are far more stable than primary methyl. With SN1, you want to be aware of weak nucleophiles, so some really common examples are water, alcohols, and carboxylic acids, but we should mention that you are directly competing with E1 when you're involving SN1. And so the distinguishing factor between the two is if there's heat or not. If there's heat, it goes E1. If not, SN1. So now we're going to look at a comparison chart, but before we do that, we should mention that the one similarity between SN1 and SN2 is that you need a good leaving group, which typically manifests in the form of halides. If you have an alcohol, you're going to need to convert that to a tosylate beforehand. So in terms of substrates for SN1, you're going to have tertiary react the fastest, then secondary, which is basically equated to benzylic, which is basically equivalent to allylic, and then which is much faster than primary and much faster than methyl. From there, your nucleophile is going to want to be very weak. And your solvent is going to be polar protic in the sense that it can form H bonds. And so some good examples of that would be methanol or water. And solvolysis will occur with these. The rate law, since it's a two-step reaction, the rate law and the rate determining step only involves the substrate. And so the nucleophile, unlike an SN2, does not really matter here because the only thing needed to overcome the activation energy is a substrate, or in our example, the bromobutane. Product stereochemistry will be racemization. And as we can see in the energy diagram, we have 2 transition states, sometimes 3 if you have the deprotonation step, and you'll see the carbocation intermediate formed.
Okay, so for SN2 reactions, as previously mentioned, a methyl group is best. And then it's followed by a primary, and then secondary, and after that the reaction tends not to occur, undergoing SN2 mechanisms. So for the nucleophile, as mentioned, you will want a strong nucleophile. For the solvent, this typically happens in a polar aprotic solvent, meaning it does not have the ability to hydrogen bond. Aprotic. Some examples of this are DMF, DMSO, and acetonitrile. Okay, and for the rate law for this reaction is rate equals K of both the substrate and the nucleophile. And then for product stereochemistry, you will have inversion of stereochem. So from an R group to an S group or vice versa. And for our energy diagram, there is only one, it shows only the transition state, so there is only one hump in the energy diagram. So for some practice problems, for the first one, it will undergo SN2 reactions because it is a strong nucleophile. It has a primary halide and it is a aprotic solvent. So the reaction will proceed and the result will be the following. And we are not showing stereochemistry on this, but remember if we did, it would be inversion. Okay, and so for B, this undergoes SN1 reactions because it is a tertiary halide and it is a weak nucleophile, so the product would look like this.
And we understand that there can be some confusion about what constitutes as a strong nucleophile or weak nucleophile. So here we have methanol, which is actually a very, very, very weak nucleophile. And for our substrate, it's secondary. And secondary is interesting because it can really go either way depending on the nucleophile and the reaction conditions. But in this case, given the sense that our nucleophile is methanol and we don't have heat, it's going to proceed in an SN1 fashion. So our final product, and remember that since with an SN1 you can have a carbocation, and in this case the carbocation will rearrange to form a product that looks like this. And this is just to show that there's racemization, so you've got the plus and minus of this. For this one, this is methoxide, and methoxide is very strong. And we have a primary halide, which leads me to believe that it's going to be an SN2 reaction mechanism, which will end up looking like. And so here are citations. A special thank you to Dr. Stensis, our notes that we consulted, and the textbook, and yeah.